basically we have to go in the mechanical properties of solids and fluids with us. So the name of the unit with you is properties of bulk matter. So this is of course a new topic with you, and we are going to discuss in detail one by one about the solids and fluids. So mechanical properties of the solids and fluids are to be taken in detail in this unit. Because if I talk about the matter in general, then when I talk about the matter, it means it is having solid, liquids and gases. Liquids and gases, they collectively are known as fluids, the things which can flow. Solids we have discussed in the previous chapter also. All the rigid bodies, solid bodies, they are rigid bodies. Then we discussed about the rotational motion. We discussed about the translational motion. If we make the body to move along a line, we make the body to rotate about the axis. Now, if we go in detail of the mechanical properties of the solids, then we may take a spring-like model with us, like we are having the different molecules which are separated by a certain distance. Of course, these distances are very small, but just to show you, I'm making it like this. And here I'm having a spring-like structures by which they are joined. So there are always the intermolecular forces between the different molecules is there. So when I go in detail of these intermolecular forces between the atoms, between the molecules of any solid body, this is the graph with you for the intermolecular force with the interatomic or intermolecular distance. And this distance, see here the force is negative, means attractive force. And this force is positive, means the repulsive force. If you want to do the graph plotting between the potential energy and the intermolecular distance, then it will come like this. At this point, the potential energy is minimum. Shape of the graph is same, but this distance, which is R0, is termed as the equilibrium distance. This is, Bache, we are going in the internal structure of the solids. When we are talking about the solids, it consists of atoms or molecules. Of course, three-dimensional diagram we can make. And we talk about the intermolecular or interatomic distances. When we talk about the intermolecular forces, then of course intermolecular forces we have already discussed with you, that intermolecular forces, they can be cohesive, they can be adhesive forces. Between the similar type of molecules, cohesive forces are there. Between the different type of molecules, adhesive forces are there. Now, if I'm going within a substance, I am talking about the intermolecular forces or the interatomic forces that is varying with the distance. So if it means they are very apart, they are having the attractive force at a particular value of the interatomic distance r, this force is becoming 0. That distance we call it as the equilibrium distance. And at this distance, if you see, the potential energy is minimum. About the mechanical properties, actually basically we have to talk about the mechanical properties, and this is finding a lot of application with you in the day-to-day life. When you go with the solids, properties of the bulk matter should be clear, and the important property with you is elasticity. It means now when I'm applying the force, that force which is not bringing the linear motion, not bringing the rotational motion, but I'm applying the force, and that applied force is changing the configuration of the solid body. It means if I'm applying the force, this is I'm not able to break, of course, but it's a solid body. But if you are having a rubber like thing, if you stretch, you can see the body is able to regain when you release the body from its by after the application of the force, means when you remove the force, then the body is able to regain its original configuration. Like you can have any rubber with you, simply you can stretch it and then you can release it. So the we are bringing the change in the internal configuration of the substance, and this property by virtue of which it tends to regain its original shape or size after the removal of the applied forces, that is known as elasticity. So elasticity is the property of the body by virtue of which it tends to regain its original shape and size when applied forces are removed. These applied forces, you may call it as the deforming forces. Deforming forces, because we are applying the force simply to change the internal configuration of the substance. So we are bringing some elastic deformation in the body, and that is why this applied force is termed as the deforming force. And whatever change we are bringing in the body by applying the deforming forces, that is known as elastic deformation. So if a body you are applying the force and you are able to bring it back after the removal of the deforming forces, that body we will be calling it as the perfectly elastic. But if we are not able to regain its original configuration after the removal of the deforming forces, then the body is termed as perfectly plastic body. Like if I'm able to, I can break it, but I cannot stretch it. So that means this body is a plastic body. So we cannot change its configuration. That body is the perfectly plastic body. In nature, we are having the bodies which are lying in between the perfectly elastic and perfectly plastic bodies. Of course, and I can term the property as the plasticity. For the perfectly plastic bodies, the property due to which it is not changing its original shape or size even after the remove on applying the deforming forces, then that property we will be calling it as the plasticity. As I said, in nature we are having the bodies which are lying in between the elastic and plastic. Like rubber is an elastomer. Steel is an elastic body. You can take glass as the plastic body. Quartz, glass can be taken as the plastic bodies. And elastic body, you may take any metals with you. We can take like steel. Of course, when you do the experiment, you learn the things more, and that is done by young scientists. So this that is stress. Stress is the new term with you, which is if I'm applying the force, like you have done the experiment with the spring. So that you can take as an example here, that is made up of steel only. This spring is made up of steel, and if I am applying the force, weight is acting in the downward direction, and as a result your spring is getting stretched and extension is produced. You have done the experiment also to read the value of the extension when I'm applying the force. I'm changing the force, extension produced is getting changed. So when I'm applying the force, this weight I'm applying the force, this is the direction of the applied force. And restoring force is always produced in a direction opposite to the applied force. Now, if I'm taking this restoring force which is acting on the body per unit area, that is termed as stress. So stress, if you have to define, it is defined as the restoring force acting on a body per unit area. But you should be knowing restoring force, it is equals to the applied force. Applied force here, when we are talking in elasticity chapter, means mechanical properties of solid. This means we are talking about the deforming force, because we are not bringing the change in the motion, or means I'm not giving any rotational or translational motion to the body. Of course, solid bodies, they're rigid bodies, but we are not talking about the translational and rotational motion. We are simply applying the force to change the internal configuration of the body. And that is why we are calling this applied force as the deforming force. So when I talk about the stress, that is simply restoring force applied on a body per unit area. So if you want to write the units, of course, force is in Newton, area is measured in SI unit in meter square. You can write Newton per meter square, or which is equivalent to the Pascal unit for the pressure, and in CGS it is time per centimeter square. Dimensional formula, if you take, that is mlt minus 2 divided by area, means L square. So we are getting ml minus 1 t minus 2. So this is about the units and dimension of the stress, which is of course taken as a scalar quantity. And with you is normal stress. Types of stress, if you write, first category with you is, that is normal stress. It means I'm applying the force. Normal means perpendicular to the area of cross section. If this is the wire, this is just an enlarged view of the wire, then this is the area of cross section of the wire. Then if I'm applying the force normally, I'm applying the force, I'm pulling it both the sides. Here also I can apply the force normally. Then I'm simply increasing its length. If I stretch it outwards, then the normal stress, which is bringing the change in the length or increasing the length, that is known as tensile or longitudinal stress. While if you apply the force normally, but in the opposite direction, it means this is the wire with me and I am applying the force this direction, then I am compressing the wire. It means I am decreasing the length of the wire. Then this normal stress, I call it as the compressional stress. So if I am increasing the length, that is simply tensile or longitudinal stress. If I am decreasing the length by applying the normal stress, that is your compressional stress. So of course, the formula, basic formula is same. So even if the formula for tensile or compressional stress is to be written, you can simply write it as the longitudinal stress also, that is force upon area. And if I'm having a thin wire of radius r, diameter d, of course, because you know diameter of the wire, that is equals to twice of the radius. So whatever way you can write it in the formula, area is given by pi r square, or you can say pi d square by 4. And units will be same, Newton per meter square. Now if I'm having some body which is kept in some fluid, in some liquid, it means I'm having a spherical ball, you are putting it into the liquid. Again, force is acting normally, but that is bringing the change in volume. And then because we are putting it in some liquid, like even in air, air is also fluid. So you can take it as the hydraulic stress. Hydraulic stress is also given by force upon area, which is bringing the change in volume. So you may call it as the volumetric stress also. So if you are bringing the change in the length, that is tensile stress, you are bringing the change in the volume, that is volumetric or hydraulic stress. Applying the force such that you are able to change the area. Like if I'm having this notebook, I'm applying the force, I'm simply moving the front sheet, but the base is kept fixed. So then in that case, the stress which is acting is known as shearing stress and is given by this small change in the area. Because we are applying the force tensile the surface, so we are calling this stress as the tangential stress. So this is the value of the force which is acting tangentially, not normally. So these are different type of stresses with us. And when I'm applying the stress, then I'm bringing the change in the configuration of the. So now if I take the ratio of the change in configuration to the original configuration, that is a new quantity with you, which is termed as strain. STRAIN. Strain is the new physical quantity with you. Change in configuration to the original configuration, that is termed as strain. And here if I talk about the longitudinal strain, it means that I'm having a thin wire with me. I'm applying the force, I'm changing its length. Initially if the length is L and the change you are bringing delta L, then in this ratio delta L upon L can be termed with strain. So because length upon length is the ratio of the length, so it is a unitless, dimensionless physical quantity. So strain is a unitless, dimensionless physical quantity with you. Now, if I'm bringing, like as I said, that I'm having a body and whose volume I'm decreasing by putting it in some fluid, then I'm bringing the change in volume. So change in volume to the original volume, that is the stress. So volumetric strain, that is simply the change in volume to the original. So depending upon what type of change you are bringing, we have simply named the strain according to that. That's longitudinal. If the tensile or compressional stress is there, then the strain which is produced is your longitudinal strain, because the change in length is brought with respect to the motion. You are bringing the change in volume to the original volume, that is volumetric strain. And shearing strain, as I said, you are bringing the change in this delta theta, that is the change which is again given by simply this displacement delta. So again delta L upon L. So it means also you can say theta. So I can have these three type of strains with me, depending upon the stresses which are provided. Experiment which we have already done with Hooke's law experiment, that I'm applying the force and I'm removing the force, and I got my readings were coming same for the extension. So within that limit, if I do the graph plotting for the load applied and the extension produced, they both are coming directly proportional, which is your Hooke's law. That extension produced, that is directly to already you people have done that the restoring force is directly proportional to the extension produced. Negative sign is simply because restoring force acts in opposite direction to the force your extension produced. So F, I can write it as minus kx, where k is the spring constant. This you have already done. This is simply to revise. Now, if I'm applying the force which I'm going beyond a limit, then your graph is not coming a straight line. Means then that means I have gone beyond the elastic limit. So what is elastic limit if I have to define? It means the maximum force which I can apply to a body up to which the body behaves like an elastic body. And if I'm going beyond, if I apply the force beyond that maximum force, then the body will not behave like an elastic body. Rather, it will become a plastic body, means it may break or it may not able to regain its original configuration. So elastic limit is the limit up to which the body regain its original configuration after the removal of the deforming forces. And Hooke has performed the experiment within elastic limit, and he said that extension produced is directly proportional to the load applied. Of course, restoring force is same as the load applied but with negative sign. Now, on the basis of this only, when we are dealing with solids, now the same thing I can write, because we have done that when I'm applying the load is being applied on a body that is producing the extension, and load applied per unit area is bringing the strain in the body, that is to change in configuration to the original configuration. So this is simply the another way of writing the Hooke's law, which said that within elastic limit, this line is important, beta, that within elastic limit we are talking. It means up to the limit, when I'm applying the force, I'm removing the forces, I'm getting coming back this line. It means the elastic behavior is being obeyed. So this is the maximum value of force you have to decide by knowing the elastic limit of a particular material. Then it is found that stress is directly proportional to strain, or you can say strain is directly to stress and vice versa. And if I remove the proportionality constant, I am getting stress E into strain, and this E I can call it as the modulus of elasticity, which is again a very important term with you. Modulus of elasticity, that is termed as the ratio of stress to the strain. So because strain is a unitless quantity, so the units for the modulus of elasticity will be same as that of stress. It means Newton per meter square. Or you can write the dimensional formula also will be same stress, that is ml minus 1 t minus. So this is a new term with you, that is modulus of elasticity, which is simply the ratio of stress to strain. And this you need to note down. This formula is important for you, that is denoted by E. And units and dimensions will be set up. Depending upon what type of stress I am giving and what type of strain is getting produced, I have three types of modulus. Like if I am having the wire of length L, I am applying the force, I am changing the length extension delta L, then this force is acting normally. So I may write Young's modulus of elasticity. In place of E, I am simply writing Y for Young's modulus, which is equals to normal stress to the longitudinal strain. So normal stress means force upon area, and strain is delta L upon L. Area of course for a given wire, if R is the radius, then you can replace area by pi R square. And this experiment was done means by Young, taking the wire, and we can take any material and we can find its Young's modulus of elasticity simply by noting down the extension produced on the application of the force. It means like the spring, we can have a load can be applied here. We can note the change in the area of cross section by stretching the wire, and of course we take a very lengthy wire, means at least 1 to 2 meters long wire we take, and then extension produced comes in millimeters only, And then we decide, by having this knowledge of Young's modulus of elasticity of different materials like iron, steel, we are using them in making the various bridges. So this is finding a lot many applications in day-to-day life, Young's modulus of elasticity. Of course, units will be same, Newton per meter as of the modulus of elasticity. And if I'm having a bubble, or I'm having a ball, spherical ball, which I'm putting in water, then again the normal stress is there, but bringing the change in volume, then the modulus of elasticity which is coming is known as bulk modulus of elasticity, which is denoted by B, capital B. After the name of the scientist only, these symbols we are using. So normal stress is again force upon area, and as you can see, the volume is decreasing by applying the force. So negative sign is simply taken to show that the volume is decreasing, decrease in volume to the original volume. And you can write this formula, that is with negative sign, FV upon A delta V, or F upon A you can replace by pressure P, because here the pressure, hydraulic pressure we can say, is acting on the body because of the water. And the term also is coming many times, which is simply the reciprocal of bulk modulus of elasticity. So we are having the standard values for the different materials, bulk modulus of elasticity and compressibility of different materials, which is again finding a lot many application in designing the ships. So, Young's modulus and bulk modulus, of course, for a perfectly rigid body is infinite. It means they cannot be deformed. But in general, we don't have the perfectly rigid bodies. We are having the bodies, as I've said, between the elastic and the plastic bodies. So, no perfection is there in the real when we go with the different materials. So, they get deformed on applying the forces. Third with you is modulus of rigidity, or you can say the shear modulus. On the basis of the shear stress, shear strain, you can call it as the shear modulus of elasticity, which is simply denoted by eta, or you can write it by G also if you want, but most of the times I'm in a habit to denote it by eta. So you will also find the same symbol, eta, for the shear modulus of elasticity, which is the ratio of the tangential stress to the shearing strain. So when I'm having this fixed place, of course, I'm applying the force tangentially on the upper surface, and I'm bringing some shift is there in the upper surface with respect to the fixed face. And this theta or delta theta can be noted. So theta will be, of course, delta L upon L, and I'm applying the force F if A is the area I'm having. Then can write G or eta equals to F upon A divided by theta, where theta is delta L upon L. So this is about the shear modulus, which we talk about in for the various materials when we have to make the sheets. All these properties, malleable and which materials are ductile, all these properties are decided on the basis of having the knowledge of elasticity of different materials. Of course, if you go with the ideal liquid, eta is 0, because liquids at rest, they are not able to sustain the tangential force. So this is having the tangential force, that is why tangential stress, the name is there. And the modulus of elasticity is shear modulus of elasticity. So keep things up to this for today. Thank you everyone.